For a long time, the phrase Tesla's cheapest model meant something very different from what it means today. It used to point toward vehicles sitting near $40,000. It's often paired with the unspoken reality that battery degradation would slowly eat away at performance within a few short years. That narrative is now being completely rewritten. Elon. Musk has officially unveiled the 2026 Tesla Model 2 with a starting price of just $15,999. Powered not by lithium-ion, but by aluminum-ion battery. Technology that promises 10-minute charging and a service life, measured in decades rather than years. This isn't a distant concept car or a lab prototype. Tesla claims this vehicle is production-ready. That changes everything. The real question is not whether the Model 2 is affordable. The question is whether this battery chemistry can actually perform at scale in real-world conditions across millions of vehicles. And if it can, the implications for the global automotive industry are enormous. The Model 2 is physically smaller than anything Tesla has sold before. Measuring just over 4 meters in length, sits roughly 45 centimeters shorter than the Model 3. That difference may sound minor on paper, but in dense urban environments, it is the difference between endlessly circling a block and slipping into a parking space on the first attempt. Tesla's internal data analysis, drawn from cities like San Francisco, New York, and Boston, showed that nearly 1/3 of available street parking spaces fall just below the length threshold of most modern EVs. Tesla didn't shrink the vehicle simply to cut costs, they shrank it to solve a problem. Urban mobility is constrained by space, not just by energy. By optimizing the Model 2's footprint,
Tesla
is directly targeting the daily friction points that frustrate drivers in crowded cities. Despite the compact exterior, interior utility has not been sacrificed. The Model 2 delivers approximately 420 liters of storage capacity, rivaling many mid-size sedans. This is made possible by the flatter architecture of the aluminum-ion battery pack, which occupies less vertical volume than traditional lithium designs. That space efficiency allows for more usable cabin and cargo volume without expanding the body dimensions. Weight reduction is another major factor. Tesla is targeting a curb weight under 1,300 kilograms, which is roughly 500 kilograms lighter than a Model 3. That is equivalent to removing the mass of 5 adult passengers from the vehicle structure. This reduction fundamentally changes the driving dynamics. Less weight means faster acceleration, shorter braking distances, improved handling response, and higher overall efficiency. Aerodynamics complete the efficiency equation. Tesla projects a drag coefficient around 0.20, which translates into meaningful energy savings at highway speeds. Even a 6% reduction in drag can add 15 to 20 kilometers of real-world range without adding a single battery cell. Achieving those gains requires thousands of hours of computational modeling, tunnel testing, and micro-adjustments to body contours and airflow channels. But all of these design decisions serve a larger goal. The real disruption comes from what sits beneath the floor. Tesla is moving away from lithium-ion chemistry and toward aluminum-ion. On paper, the advantages appear almost too good to be true. Aluminum is the third most abundant element in the Earth's crust. It is inexpensive, widely available, and not concentrated in geopolitically sensitive regions the way lithium is. By shifting to aluminum-ion, Tesla claims it can reduce raw material costs by up to 90%, while eliminating dependence on Chinese-controlled lithium supply chains. The economic implications are massive. Current lithium-ion battery replacements can exceed $15,000. Tesla estimates that aluminum-ion replacements could cost under $3,000 even after decades of use. That difference alone could determine whether an EV is cheaper or more expensive than a gasoline vehicle over its lifetime. Durability is where skepticism naturally arises. Tesla projects more than 20,000 full charge cycles with minimal degradation under typical driving patterns. That equates to over 2 million kilometers of use. By comparison, conventional lithium-ion packs often show significant capacity loss after 1,500 to 2,000 cycles. If Tesla's projections are accurate, A single aluminum-ion battery could outlast 10 traditional EV battery packs. That longevity changes ownership economics entirely. Instead of budgeting for a major battery replacement after several years, owners could realistically expect the battery to last longer than the vehicle itself. Charging performance adds another dramatic layer. Tesla claims the Model 2 can charge from 0 to 100% in approximately 10 minutes, using its next-generation 300-kilowatt infrastructure. That is faster than most people spend at a gas station. Thermal stability is also significantly improved, with efficient operation from -40 to +60 degrees Celsius, reducing the need for complex cooling systems and improving reliability in extreme climates. There are trade-offs, of course. Aluminum-ion cells currently exhibit about 20% lower energy density compared to lithium-ion. Tesla counters this by leveraging the substantial weight reduction of the vehicle and improvements in motor efficiency. In pure range terms, this is not about beating every competitor. It is about achieving sufficient range while dramatically improving cost, safety, and lifespan. This reveals Tesla's real strategy. They are no longer fighting a range arms race. They are building a platform optimized for durability, affordability, and total cost of ownership. If EVs suddenly last 2 or 3 decades with minimal performance loss, the comparison to internal combustion vehicles becomes almost unfair. Gas cars require regular maintenance, oil changes, transmission servicing, exhaust system replacements, and eventually engine overhauls. The Model 2 is designed to eliminate most of those failure points entirely. This also forces a shift in how consumers think about vehicles. Instead of disposable products replaced every few years, cars begin to resemble long-term assets. A Model 2 could realistically serve multiple owners across its lifespan. With the same battery pack still delivering reliable performance, the manufacturing implications are equally important. Aluminum-ion cells are structurally simpler and require fewer exotic materials. It simplifies supply chains, reduces production volatility, and enables faster scaling. Tesla's move toward gigacasting and modular battery integration further reduces part counts, assembly time, and labor complexity. This is how a $15,000 EV becomes possible without sacrificing margins. Cost reduction is not coming from removing features, it is coming from redesigning the entire system. Safety benefits also deserve attention. Aluminum-ion chemistry is inherently more thermally stable and far less prone to thermal runaway. This significantly reduces fire risk, one of the most common concerns surrounding EV adoption. Combined with Tesla's structural battery pack design, the Model 2 achieves improved crash protection while using less material. From a macro perspective, the shift away from lithium reduces pressure on environmentally sensitive mining regions and lowers the ecological footprint of battery production. Aluminum recycling infrastructure is already mature globally, further enhancing sustainability. The remaining question is validation. Laboratory results are one thing. Mass-produced vehicles operating in diverse climates, usage patterns, and charging behaviors are another. Tesla's projections are ambitious, and history shows that the company is not immune to over-optimism. However, even if real-world performance achieves only a portion of these claims, the Model 2 would still represent a substantial leap forward compared to current EV technology. Consider the broader market impact. If Tesla can deliver a reliable, long-lasting EV at this price point, legacy automakers face a serious dilemma. Their cost structures are built around internal combustion complexity, multi-speed transmissions, and global fuel distribution networks. Matching Tesla's economics would require a complete re-engineering of their platforms and supply chains. Consumers, meanwhile, gain access to electric mobility without financial barriers. For many households, a sub-$16,000 vehicle with ultra-low operating costs becomes not just competitive, but clearly superior to gasoline alternatives. Urban environments benefit as well. Smaller, lighter, more efficient vehicles reduce congestion, lower energy demand, and improve air quality. The Model 2's size is not a compromise. It is an optimization for the realities of modern cities. there is also a long-term societal effect. When transportation becomes cheaper, cleaner, and more durable, mobility expands. Economic participation increases. Access to employment, education, services becomes less constrained by fuel costs and maintenance expenses. In that sense, the Model 2 is not just a car, it is infrastructure. Of course, Tesla's credibility rests on execution, scaling aluminum-ion production, deploying ultra-fast charging networks. Maintaining quality at high volumes are non-trivial challenges. Any delays, cost overruns, or performance shortfalls will quickly attract criticism. But the direction is clear. Tesla is not merely improving EVs. They are redefining what a car is expected to deliver over its lifetime, if the Model 2 performs. As promised, the era of EVs being seen as expensive, short-lived alternatives to gas cars ends. And once that shift in economic logic becomes obvious to the mass market, the competitive landscape changes almost overnight. Automakers are no longer judged by horsepower figures or trim packages. They are judged by lifetime costs per kilometer, reliability over decades, and how little friction their vehicles introduce into daily life. In that environment, the Model 2 becomes less of a product and more of a financial instrument. Think about what happens when a vehicle no longer depreciates rapidly because its most expensive component, the battery, does not meaningfully wear out. Traditional cars lose value as mechanical components age, tolerances loosen, and maintenance costs rise. The Model 2, by contrast, is designed around solid-state-like durability without the manufacturing complexity of true solid-state cells. If the battery remains stable, and the powertrain has only a fraction of the moving parts of an internal combustion engine, the depreciation curve flattens dramatically. This has profound implications for the used car market, instead of high mileage. Vehicles being viewed as liabilities, they become viable, long-term transportation assets. A 10-year-old Model 2 with hundreds of thousands of kilometers may still retain the majority of its functional value. That creates a secondary market that is both affordable and reliable, accelerating EV adoption far beyond the new car segment. Insurance models also shift. Lower mechanical failure rates, reduced fire risk, and simplified drivetrains translate into fewer catastrophic losses and more predictable repair profiles. Over time, this pressures insurers to reduce premiums, further lowering the total cost of ownership and reinforcing the economic advantage of electric mobility. Fleet operators are perhaps the most immediate beneficiaries. Delivery services, ride-hailing, platforms, municipal transport agencies, and corporate vehicle pools operate on razor-thin margins. Fuel and maintenance costs dominate their budgets. A vehicle that can operate for millions of kilometers with minimal servicing becomes transformative. The Model 2's fast charging capability allows near-continuous operation, reducing downtime and increasing asset utilization. In dense cities, where emissions regulations are tightening and congestion charges are expanding, the Model 2's compact footprint and zero-emission operation become strategic advantages rather than mere conveniences. Parking efficiency, maneuverability, and low operating noise all contribute to smoother urban integration. From a manufacturing standpoint, Tesla's approach signals a departure from incremental optimization and toward systemic simplification. The aluminum-ion battery pack is not merely a different chemistry. It enables structural integration, part reduction, and thermal management simplification. Combined with GigaCast body sections and modular electronics, the vehicle becomes easier to assemble, easier to service, and easier to scale. This is how Tesla compresses cost without compressing capability. Complexity is the enemy of affordability. Every eliminated part reduces not only material expense, but assembly time, quality, control burden, and supply chain vulnerability. The geopolitical implications are equally significant. Lithium, cobalt, and nickel supply chains are concentrated in regions subject to political instability and strategic competition. Aluminum, by contrast, is globally abundant and supported by mature, refining, and recycling ecosystems. By pivoting to aluminum, Tesla insulates itself from resource nationalism and price volatility that could otherwise constrain EV expansion. This also alters its national energy strategies. Countries that previously lacked domestic lithium resources can still participate fully in EV manufacturing and deployment. This democratizes electric mobility production and reduces dependence on a small group of mining regions. There is also a psychological component to this transition. One of the persistent barriers to EV adoption has been anxiety around battery degradation. Consumers fear that performance will erode invisibly, leaving them with a compromised vehicle long before the rest of the car is worn out. If aluminum-ion batteries truly maintain capacity over tens of thousands of cycles, that anxiety largely disappears. The ownership experience becomes more predictable. The vehicle behaves the same in year 15 as it did in year 1. Planning. Horizons lengthen, confidence increases. This stability encourages a different relationship between owner and machine. Instead of constant concern over wear, maintenance schedules, and resale value, the focus shifts to usability and convenience. The car becomes a tool rather than a liability. Infrastructure planning also evolves. Ultra-fast charging reduces the need for oversized battery packs. Instead of carrying excess energy capacity at all times, vehicles can rely on rapid replenishment. This lowers vehicle mass, material usage, and cost, while improving efficiency. Charging stations become closer in function to traditional refueling points, with high throughput and short dwell times. Grid integration benefits as well. Aluminum-ion cells' thermal stability and cycle life make them well-suited for bidirectional charging and vehicle-to-grid applications. A fleet of Model to South could collectively function as a distributed energy storage network, smoothing demand peaks and supporting renewable integration. In that context, the car is no longer just a consumer product. It becomes part of the energy infrastructure. This raises broader economic questions. When transportation and energy systems converge, value chains overlap. Automakers become energy companies. Utilities become mobility partners. Software becomes as important as hardware. Tesla has positioned itself at the center of this convergence. The Model 2 is not simply an entry-level vehicle. It is a node in a larger ecosystem of charging, storage, autonomy, and grid interaction. Autonomy, in particular, amplifies the impact. A durable, low-cost, long-life vehicle is the ideal platform for shared mobility. If a single car can operate reliably for millions of kilometers, it can support continuous service across multiple users, dramatically reducing the number of vehicles required to serve a given population. This has implications for urban planning, parking infrastructure, and land use. Fewer privately owned vehicles mean less space dedicated to storage and more space available for housing, green areas, and public amenities. Environmental benefits extend beyond tailpipe emissions. Lower material turnover, longer product lifespans, and improved recyclability reduce the overall resource intensity of transportation. Sustainability becomes embedded in durability, not just an energy source. Critics will rightly point out that laboratory performance does not always translate cleanly into mass production. Scaling new chemistries involves yield challenges, quality control issues, and unforeseen degradation mechanisms. Tesla's history includes both rapid innovation and aggressive timelines. But even partial success shifts the baseline. Delivers even half of the promised cycle life and cost reduction. Still represents a meaningful advance over existing technology. The competitive response will be telling. Legacy automakers are constrained by existing platforms, supplier relationships, and capital allocation priorities. Re-engineering around a new battery chemistry requires not just technical change, but organizational transformation. Those who move slowly risk being priced out of the mass market. Those who move quickly face execution risk. Tesla, unburdened by legacy architectures, can iterate faster. From the consumer perspective, the choice becomes increasingly clear. When an electric vehicle is cheaper to buy, cheaper to operate, safer, quieter, more reliable, and longer lasting than a gasoline car, The rationale for internal combustion weakens to the point of irrelevance. At that moment, adoption accelerates. Not because of policy mandates, but because of rational self-interest. The Model 2, therefore, is less about competing with other EVs and more about displacing the entire concept of combustion-based personal transport. This is why the question of overpromising matters. Expectations shape markets. If Tesla delivers close to what it claims, the psychological barrier to EV adoption collapses. If it falls short, skepticism will linger. But the direction of travel is unmistakable. Materials, science, power, electronics, manufacturing automation, and software integration are converging toward vehicles that are simpler, more durable, and more efficient than anything that came before. In that future, the car is no longer a complex mechanical device that gradually wears itself out. It becomes an electrically driven platform whose lifespan is limited primarily by structural fatigue rather than by consumable components. That is a fundamentally different paradigm, and once that paradigm is established, it is difficult to reverse. The economics favor it. The infrastructure adapts to it. The consumer expectations align with it. The 2026 Model 2 may be remembered not just as Tesla's cheapest car, but as the point at which electric vehicles stopped being an alternative and became the default.